We have the first presentation from Jin. Jin is a assistant professor in EECS department at the University of California, Irvine. His research focuses on hardware-software co-design of AI accelerators for emerging workloads such as augmented and virtual reality. He was a research scientist at Meta in Reality Labs before joining UCI, and he received his PhD in CS at the Georgia Institute of Technology in 2020. So let's welcome the first speaker.
Okay, thank you for your introduction. Okay, hello everyone. Welcome to my talk. So my name is Hyoukjun Kwon, and I'm going to introduce our work, DREAM, a dynamic scheduler for dynamic real-time multimodal ML workloads. And this work was a collaboration work with UC Berkeley and UCI and Meta. Today, we have new class of ML workload emerging, so what we term as real-time multimodal or RTMN workloads. As an example, let's take a look at the social interaction B usage scenario from XR bench. So this application draws AR emoji based on the action of the opponent. To implement those functionalities, we first need an eye pipeline because we need to understand where a user is looking at so that we can draw the AR object to the right location. And then we also need action segmentation because it is action-based emoji. What we can observe here is in XR bench model, eye tracking is implemented via two models cascaded like this, which has dependency. And we can find concurrency as well. We have multiple ML pipelines running together concurrently. And this is a real-time application. Each model has their target FPS numbers, such as 60 FPS. Likely, we see these kind of workloads more and more. So examples include AR/VR, not only AR/VR, but also autonomous driving and drone applications. And they impose very interesting new characteristics and requirements to the ML system design. As a characteristics, they include concurrent and cascade models inside their workload. And because they target multimodality, the models are very heterogeneous. And they often require real-time processing and targeting energy-constrained device form factors, such as wearable or embedded. And their workload is heavily dependent on the user input and the context around it. For example, if a drone is flying in the mountain area or the indoor area, the models we need to run will be pretty much different. In this work, we considered everything, but focused on the impact of the dynamic behaviors. So the last two characteristics introduces the dynamic behaviors. And in our evaluation, we found optimizing for dynamic behavior result in this much, more than 30% impact on the real RTMM, the deadline violation and energy consumption. Then we took a look at those characteristics, but what's the exact implication to the scheduler? From the cascaded models, we get data and control dependency in model granularity. And concurrent ML pipeline, we need to be careful about the starvation. If we drop frame of the specific ML pipeline, then we can get starvation. And they require real-time processing, which means we have deadlines for the designated FPS requirement. And device form factor, they are targeting embedded or wearable, so energy constraint. And dynamic behaviors, basically. So either triggered by user inputs or the context around the device. So I've been highlighting the dynamic behaviors, but how do those dynamic behaviors look like? So here's some taxonomy based on their granularity. So dynamic behavior could be in task level. As an example, the application change. The user was playing an AR game, but suddenly received an AR call from the friend. Then the set of models we are running completely changes at that moment. Another granularity is the model level. So as I showed as an example at the beginning, so there can be control dependency based on between two models. So the hand tracking pipeline only runs the hand tracking model when the hand is detected in the scene. So this is one example. And there are many optimizations proposed in the operator level, which introduce the operator level dynamic behaviors. Examples include the supernet switching or early exit and so on. So again, considering those kind of dynamic behavior has significant implication. So considering those dynamic behaviors and all the other requirements, so how do we build a scheduler for targeting this new class of ML workload? our approach is based on the composable scheduling score. We first define 4 unit scores. Urgent score, how tight is the deadline based on the current execution status. Latency preference score, when you have multiple accelerators, which accelerator is faster for each operator layer. Starvation score, how long has each ML pipelining been waiting for getting the computation resource? And energy score, what is the expected energy consumption? So all of these unit scores reflect the important aspects of the RTMM requirements. So they are all formulated in 0 and 0,1 range for composability, and everything is formulated as higher is better. So these two helps making the score composable, and it thoroughly considers all the RTMM requirements, except for the dynamicity here. So how do you capture the dynamicity in this formulation? We add the dynamic parameters when we compose a comprehensive score using all of these unit scores. So let me go over each term. So first term is capturing the real-time requirements. And the second term is capturing the starvation aspect for the concurrency. And the last term is capturing the real energy as device form factor. I'm sorry about the typo here. But here, as you can find here, so there are 2 parameters, alpha and beta. So they are runtime tunable parameters for adaptivity for the dynamic behaviors. And we utilize this to deal with the dynamic behaviors in the workload. So we have those mechanisms, but how do we tune those parameters? Our approach is using the major RTMM metrics, which are deadline violation and energy consumption. You may be curious, why deadline violation? Mainly because it's a real-time workload. Reducing the latency beyond the deadline doesn't directly help with the overall system performance. So that's why we are using deadline violation targeting real-time workloads. And we combine those as something EDP-like, energy delay product-like metric targeted for RTMM, and define a new metric, UX cost. And in addition to the deadline violation rate, we have normalized energy based on this formulation to keep the 0,1 range for composability. And this is high-level description of the parameter tuning algorithm. We set sample points around the parameter values alpha and beta, and find 2 samples that minimize the UX cost, this metric. And we compute the interpolation of those points and move on to that point and repeat that process with reduced radius for the sampling. And why do we just take the minimum point? Because we wanted to prevent being stuck in local optima. And as you can imagine, so this is inspired by the gradient descent algorithm and also simulate annealing. And how effective is this algorithm? So this is one result in our paper. So what we observed from our evaluation is the algorithm provides very fast convergence. In the worst case, 5 steps. So mostly less than 5 steps. And this example shows we can reach very near point of the global optimum very quickly. And we tested this for various workload change scenarios from system boot to the runtime workload change scenarios with all the dynamic behaviors going on within each workload. So we have more detailed technical details and result in the paper. So please refer to our paper for more details. And in addition to those scores, we also added more RTMM-oriented optimizations, which is smart frame drop. The main idea is making the early frame drop decisions when deadline violation is expected. So this is one example timeline. On x-axis, we have time, and y-axis, we list 2 ML pipelines we are using here, hand pipeline, hand detection, and face detection pipeline. And I'll not go into all the details, but we are in this time. And based on the latency estimation, so deadline violation is expected for all the frames afterwards. But if we drop the hand detection for frame 1, then we can make, although we are dropping a frame for the hand detection for once, but we can make other deadlines met like this. So as you can imagine, so this is an optimization strategy for global optimal schedule, considering those real-time requirements as this periodic inferences. And there are more considerations in this smart frame drop. So one is dependency. If we drop a model that has the dependent model, then impact is large. We avoid doing that. And concurrency, so we consider starvation when we select the smart drop model. And we make dynamic decisions whenever we receive new inference requests, and we estimate this and determine which one to drop. So with this, so we see 15.4% of UX cost reduction impact, so which shows the effectiveness of this optimization. So this is an overview of our scheduler. So let me just highlight some features. So it provides fast and dynamic scheduling, leveraging static latency and energy information obtained from the offline cost models such as Maestro or time loop. And it provides adaptivity to dynamic behaviors based on the mechanism I briefly explained in one of the previous slides. And it has RTMM-aware optimization, such as smart frame drop. And it supports multi-accelerator backend, such as heterogeneous data flow multi-accelerators, which are tailored for multimodal ML workloads. Our evaluation setting is aligned with that. So we target multi-accelerator system because they are proven effective from previous works for RTMM workloads. So we tested homogeneous and heterogeneous data flow multi-accelerator systems. And we took 5 industry-inspired workloads in AR, VR, and drone domain. And we compared against state-of-the-art scheduling algorithms. And then for evaluation study, we prepared several versions of our scheduler. The Dream Map score only performs the score-based the scheduling with the dynamic parameter tuning, and Dream Smart Drop added smart frame drop upon that, and full version includes supernet switching as a case study for showing the scheduler's capability for supporting those optimizations. And this is a snapshot of our evaluation results. So there are too many details, so let me just summarize overall results. So on average, we observed 32% and 50% UX cost improvement compared to 2 latest baseline. And I also highlighted this. So this is an evaluation study we performed, and this one means if we perform dynamic scheduling without adaptivity parameter tuning, but as soon as we tune the parameter, which means as soon as we consider the dynamic behavior and optimize for that, we see this much reduction in UX cost. On average, 32%, which is significant. So as a key takeaway, I'd like to highlight that optimizing for dynamic behavior has significant impact for the RTMM performance and energy efficiency. And there are more learnings and insights are available in the paper, so please refer to our paper for more details. And let me conclude my talk. So emerging RTMM ML workloads impose various challenges to the ML system, as you can see here. And thorough consideration of this implication of all RTMM characteristics are key for an effective RTMM scheduler. So aligned with that, we define many scores like this. And as a key takeaway, optimizing for dynamic behavior has a significant impact on RTMM performance. So the takeaway for the entire talk is we should take dynamic behaviors as a major consideration when developing hardware-software systems targeting RTMM ML workloads. So thanks for attending my talk, and I am happy to take questions.
So do we have any questions from the audience? Yes, go ahead.
Very nice talk. I'm Pete, a piece of graduate. I have actually 2 questions, one very short, same follow-up.
Yep.
First is the scheduler, the dynamic scheduler, a runtime scheduler or a design scheduler?
It's runtime scheduler. Yeah.
So that's great. How does it scale the number of models? You said you conversion steps. How many models were there?
Oh, I see. Yeah, I haven't shown the details about the models we have, but for each usage scenario, on average, we have 3 to 4 models. Yeah, so those are the typical usage we find in the industry papers.
And do you have a sense of if we had a order of magnitude larger number of models, which is the case usually in these, let's say 50 models, like how would we scale in that?
Yeah, that's a very interesting question. So I'd like to clarify first. So we are targeting kind of embedded and wearable devices, as we mentioned. So that is not likely the case, but in case we have those cases, this scheduler, maybe the applicability of this scheduler to the cluster domain, I think it should be okay. So one thing is we can hide the latency of the scheduler within the inference latency. So when the layer is running, we can make scheduling decisions and we can hide latency. So I believe there will be some tolerance up to very reasonable number of models, but I'm also curious. So what is the limit? So yeah, very good question for a very good point. Thank you.
Okay, we can quick question. Yeah, please. Yeah.
Yep.
Very nice talk. The question is related to this scheduler for accelerator. Like they have the
Yes, basically we are targeting such workloads. Yes.
Actually, the second question is more about opinions. So I'm saying, especially in this autonomous driving area, the machine learning model itself is getting to end-to-end. So do you think in the future we're gonna have actually less dynamism in the workload because these models are getting?
Yeah, that's a very good point. So there are many optimization methodologies. So it's to eliminate the dynamicity, actually we can introduce more memory and compute the overhead. So let me take one example. So mask-card CNN, for example. So based on the result of the NMS or region proposal network, we may have different number of batches in the following head. But if we just fix the head to the maximum number, for example, we can eliminate the dynamicity, but we are paying more computation for some redundant computation. So yes, those kind of optimizations are possible, but which one is better? I think it heavily depends on the context. So yeah, I think that's a very interesting question. So thanks for that.
Okay, due to the time limit, so we cannot have more questions.
Okay.
I thank the speaker again. And so the
Thank
second speaker can go to set up the slides. And I'll give the short introduction. So we have the second paper called the SoC-Flow, and the speaker is Daliang Xu, who is a third-year PhD student at the Peking University. His advisor is Professor Xuanzhe Liu and Mengwei Xu. His research interest focus on the mobile edge AI systems.
Hello everyone, I'm Daliang Xu from Peking University. Today, I'd like to share our work SoC-Flow efficient and scalable DN training on SoC-Clustered edge servers. SoC clusters are emerging form of servers, including massive mobile system on chips. Specifically, we use a commercialized SoC cluster we have deployed as a real employment as an example. It contains 6 quantum mobile SoCs and a control board. These chips are mounted on 12 PCB boards with 5 each, and these PCB boards are connected with 1 Gbps network. Its physical structure is shown in this figure, and it can deliver dense computing capacity such as 6 Snapdragon SoCs and in a 2U rack. Each chip is a mobile SoC. It has a octa-core CPU, a GPU, a Hyoukjun DSP as an NPU, and 12 GB LPDDR5 RAM. Since each SoC is same as smartphone ones, it has the same ability to run native mobile applications without any modification. So millions of them have deployed in edge servers or the base stations to serve the cloud gaming or live streaming workloads. However, from the real-world deployment traces, we have found such SoC clusters are underutilized. For instance, the average CPU usage of more than 90% of the SoC CPUs is under 20%. To that end, to harvest such free cycles, we want to perform the distributed deep learning training tasks, as training workloads are predictable and delay tolerable. We found 2 distinct challenges when doing that. The first one is the scarce network bandwidth, that is less than 1 Gbps. Usually, the network bandwidth, this network bandwidth is enough for the cloud gaming workloads, but it's too weak for distributed training workloads. Our evaluation on 32 SoCs find that a 32 SoC inter-PCB board gradient communication delay is 2.6 to 9.8 times latency than that of 4 SoCs. The second one is the heterogeneous processors with mixed data formats. Typically, a mobile SoC contains NPU for int8 operations and the CPU for float32 operations. Such heterogeneities can lead to more than 5% accuracy loss when training use both of them for VGG11 and ResNet 18 models. To solve this problem, we propose SoCFlow, the first framework that can efficiently train DN model on SoC clusters. SoCFlow takes the training data set and train neutral network as the input. Then, ahead of the training, SoCFlow will determine how the SoCs will be orchestrated, such as SoC grouping and gradients communication frequency. Then, the SoCFlow will dispatch the training data and the model to each SoC, and each SoC can perform float32-based training on CPU and int8 training on NPU, or mixed operation with both of them. It mainly includes two novel techniques. The first one is the group-wise parallelism with a delayed aggregation to mitigate the network bottleneck problem, and then the data parallel misexpression training algorithm to improve the convergence accuracy. For the first technique, our key idea is that the network capacity of the SoC cluster has lied somewhere between the high-speed data center and the wireless network. So we propose a hierarchy topology that enables group-wise parallelism. We divide SoCs in different groups. Within a group, the SoCs form a ring or reduce topology and change their model weights frequently, that is per batch. Across logical groups, the weights are aggregated in a delayed manner, that is per epoch. To achieve this, SoCFlow should first determine the group size. Typically, the per epoch training time is negatively correlated to the group number n, and the convergence accuracy exhibits a negative correlation with the group number n. So, a larger number n means a higher convergence accuracy, but with a longer training speed. So, how to trade off the group size to achieve better convergence accuracy and training speed is important to our system. Luckily, our observation find that the training accuracy observed during the initial epoch closely to the behavior of the convergence accuracy. To that end, during the warm-up stage, SoCFlow provides the training accuracy from a smaller group size to a larger one. It stops at the first group size where the accuracy falls significantly, typically to around 15%. In general, the logical group size cannot always be equal to the PCB SoC size. This situation arises because the logical group size is determined by trading off the convergence accuracy and the training speed, while the physical PCB size is determined by the hardware by the companies. In this situation, different SoC groups will contend for the scarce inter-PCB communication bandwidth, as each group has to perform communication with other PCB boards SoCs. They had to perform the per batch gradients communication simultaneously. To solve this problem, we first use Li inter, the number of the logical groups contending for inter-PCB communication, to depict the complexity of inter-PCB communication contention. Usually, a larger Li inter means more contention. Then we formulate a mapping problem to minimize the overall contention across SoC PCBs. To solve this problem, we propose integrated greedy mapping algorithm. Our key idea is that all SoCs of a logical group mapped to a single PCB board will not contend for inter-PCB network communication, such as logical group 1. So, SoCFlow first map as many as logical groups as possible to physical groups without splitting, as shown in logical group 1 to 3. Then, the rest of the logical SoCs are mapped in sequence. We have proved that such mapping method can minimize the inter-PCB communication during the intra-gradient communication, and the maximum value of the contention is 2. Nevertheless, after using the mapping algorithms, in many cases, there are still two logical groups contending for the inter-PCB contention, as shown in the theorem 2. To further solve this problem, we can divide the groups with contention into different communication groups to communicate separately in sequence to avoid network contention. The theorem 2 guarantees that in our situation, there are at most 2 communication groups. So SoCFlow uses a pipeline of 2 communication groups to hit the intra-group communication time. For the second technique, our key idea is that we can compensate the presentation of loss of int8-based training by offloading part of the training data to the CPU with float32 format. Alpha, to control how much data should be input to the int8 models, we propose 2 metrics. The first is alpha. Alpha is a confidence metric that indicates the error gap between the int8 models and the float32 models. When alpha is approaching to 1, the int8 model is more accurate, and the more training data should be fed into int8 models. Then beta is computer power ratio that represents the ratio of computing power for heterogeneous processors. When beta approaches to 1, it means NPU is more powerful. And so more data should be fed into the NPU 2. When jointly considering accuracy requirements and performance issues, we propose gamma, the max value of the e to the power of minus alpha and 1 minus beta. When e to the power of minus alpha is smaller than 1 minus beta, the NPU processing capacity is not enough and the CPU is idle. So we feed more data into NPU cannot get any benefits. The final weights are aggregated from float32 weights to int8 weights. We have fully implemented SoCFlow as an end-to-end prototype on the Android OS. We have evaluated 6 baselines on 60 SoCs, including 2 industry distributed machine baselines like Prime Server and RealReduce, and 2 SOTA research baselines, HiPress and 2D parallelism, and 2 fidelity learning baselines, FED-AVG and tree-FED-AVG. Our evaluation shows that only SoCFlow can guarantee that all training tasks finish within 2 hours, which is smaller than the SoC cluster idle time. It can achieve up to 730 times training step up. That is because our methods can mitigate the network bottleneck and fully unleash the NPU's power. When compared with the cloud GPUs, SoCFlow are more suitable for training small to medium sized models such as Mobile Night than cloud GPUs. It can reduce 10.2 times energy consumption and save half room compared with the V100 servers. The situation arises because mobile SoCs are designed for small to medium size, especially for some edge DN models. In conclusion, we have proposed SoCFlow, the first efficient DN training engine for SoC clusters. It exploits group-wise parallelism and mixed precision data parallel training algorithm. We have built the prototype and achieved superior performance over other methods. Thanks for your listening. If you have any question about SoCFlow, please ask me via this email address.
So do we have any questions from the audience? Please come to front. Thanks.
Hello. First, thank you for your great talk. And I'm Jinook from Postech, South Korea. And if the model training can be done in the device idle time, what happens when the device becomes busy? That was my question.
Okay, yeah. Thanks for your good questions. Yeah. Let me show your slides. Our training is use the group method. So we have different groups. Whenever there's some user requests coming in, we will shut down some groups so we can provide some idle SoCs to perform cloud gaming. And as we use the group parallelism, our training methods are flexible. So just kill some of the logical groups does not influence the accuracy, but it will be influence the training speed. But you know, if there are really small SoCs, so the training speed, of course, will be slow. Yeah.
Okay, thank you.
Thank you.
So, hello, Andre Brinkmann from Johannes Gutenberg University Mainz. Thank you for your talk. I've got one question. You compared the energy consumption of your cluster with the energy consumption of GPUs. Do you also have a comparison concerning the performance? So how many of your clusters do I need to more or less match one GPU?
Okay, yeah, in our experiments, we perform 40 mobile SoCs. So usually SoC cluster contains 50 or 60 mobile SoCs. Yeah. And we compared this 40 SoCs with one V100 GPU server. Yeah.
Okay, and which one is how much faster?
For some small size models such as the Night or Mobile Night, yeah, or methods will be faster, yeah. But for some larger models like ResNight 18, yeah, the V100 server will be faster. Yeah.
Okay, thank you.
Yeah.
Okay, so going to the time limit, so we all thank the speaker again, and so the next speaker, then we have the third speaker, also from Peking University, Wenfei Wu. So he's an assistant professor in Peking University. He obtained his PhD degree from the University of Wisconsin-Madison. His research focuses on computer networks and distributed systems and has published more than 50 papers in these areas. So he has won the Best Paper Award in NSDI 2021 and the Distinguished Paper Award ASPLOS last year. So let's welcome the speaker.
Yeah. Thanks for the introduction. I'm Wenfei Wu from Peking University. I'm going to talk about training job placement in clusters with statistical in network aggregation. So this work studies the RNA job placement in a shared cluster with the goal to maximize the cluster resource utilization and overall job efficiency. In data parallel training, the job spans multiple GPUs on different servers. These GPUs would perform an all-reduce operation to synchronize their model and gradients. So to accelerate or reduce a method, a primitive called in-network aggregation, RNA, is proposed. Its main idea is to offload the reduce operation onto the switch. When multiple workers send gradients to a PS, the intermediate switch would aggregate the gradients and send one copy to the downstream device. So this method can save the traffic volume and accelerate the training. RNA works. So if we turn this feature on, the job would consume the switch memory, but reduce the link bandwidth usage. If we turn it off, it does not consume the switch memory, but would consume more link bandwidth. RNA works as follows. So the switch memory is organized as an array of aggregator. So the gradient packets with the same PSN are mapped to the same aggregator and get aggregated there. So when there are multiple jobs, a method called statistical RNA is proposed. The switch memory is organized as a shared pool of aggregators. Each job's packet is mapped to an aggregator by a hash function. So it hashes the job ID and PSN. So packets of a job with the same PSN is still mapped to the same aggregator. But in this way, the resource pool is used more uniformly. So the resource efficiency is better. And also this approach can make RNA to be a transparent and service agnostic to the application. However, statistical RNA makes job placement more challenging. There are two challenges. First, the resource allocation is decentralized by each job. So the job manager
does not have a view of the resource utilization and the available resource in the cluster, so it cannot make a reasonable decision. Second, the overall search space to find a placement plan for a job is exponential. It's very large. So we propose a solution targeting these two problems. First, for a cluster with some existing jobs, we propose a water filling algorithm to estimate the resource usage and the remaining resource in the cluster. Then with this information, when we place a new job, we formulate a dynamic programming algorithm to efficiently search the placement plan for a job. For the first challenge, the problem is that there are multiple jobs sharing the cluster and they contain for two resources, the memory and the link bandwidth in decentralized manner. So what's the final state when these jobs converge? So there is a similar and classical problem in a topology with multiple TCP flows. If all the flows converge, what is their converged throughput? So the method is, the algorithm is called water filling algorithm. In RNA, the problem is more complex. There are two resources, switch memory and link capacity, and they are coupled. So we transform the switch memory usage into an equivalent throughput. So assume the switch spares n aggregators with packet size s. So the switch memory is size is ns. And in one round trip, this memory can only serve this amount of data. So the throughput A is ns over RTT. So the two resources are unified as throughput. If the sending rate does not exceed this throughput, then all traffic is aggregated. If the sending rate exceeds the PAT, we call it PAT. The remaining traffic are sent fall back to the normal sending mode. So with this transform, we can run the water filling algorithm as follows. The algorithm is iterative. In each iteration, it injects traffic into active jobs. So it also injects traffic to the links and switches that has these jobs until one link capacity or switch PAT is full. Then we freeze the full link or switch and it's traversing jobs. Then we go to the next iteration until all jobs are frozen. So finally, we can get each job's throughput, and we can also derive the remaining available resource in the cluster. So with the cluster resource known, we need to, when we have a new job, we need to find a placement plan for this job. So there are three resources: GPU, bandwidth, and number of flows of each server. So we give each server a score based on its bandwidth and flow. So when we place a job, the problem is like a bin packing problem. We need to find a set of GPU servers that can satisfy the GPU while maximize the score. So in this example, there are 6 servers. So these are their available resources. If we want to place a job with 7 GPUs, assume we want to place a job with 7 GPUs. So the method is we can build a dynamic programming algorithm. So the placement plan on S servers can be derived from the plans on S-1 servers. So we can derive a recursive function to place on S servers from the solution based on S-1 servers. This recursive function can also be used to build a dynamic programming algorithm. In the example, first example, we find a high-scoring placement plan with 2, 3, 4, 6. We place the job on these 4 servers. So we test our solution NetPack on testbed and in simulation. We run workload or VGG, LSNet and ResNet. First, we evaluate whether the resource utilization estimation method, the water filling algorithm, is accurate. So the algorithm estimated result matches the actual resource usage in the test bed, and also the simulation result and the test bed experiment has a high correlation. Then NetPack can reduce the GCT obviously. On the test bed, the GCT, we compare NetPack with other baseline algorithms. The GCT can be reduced by 13% to 45%. So we test the efficiency of the algorithm. We can complete the placement of 4,000 jobs within 100 seconds. We test the robustness of the algorithm. We set the system in different settings, such as wiring, switch memory, and different bandwidth over subscription. In all cases, NetPack outperforms the baselines. So to sum up, NetPack is a system for job placement with statistical RNA. So we built two algorithms. One is RNA water filling algorithm, which provide the estimation of the resource usage for jobs with decentralized resource allocation. Then we build a dynamic programming algorithm to generate policies to place a job, which can maximize the overall job efficiency. In the future, we can jointly consider the job placement and the resource scheduling. In the runtime, we can make the job take turns to use the resource to get a better resource efficiency. Okay, that's all about my talk. I'm happy for questions.
Do we have any questions from the audience? Please come to the front. Okay, so I have a quick question. So in your evaluation, do you consider the job manager scheduling overhead can be done at online or offline? Yeah.
Oh, yeah, that's a good question. So currently we batch the jobs, then we put the job batch by batch. But according to the evaluation, the placement algorithm can run fast enough. For example, it runs in a few minutes. Completed in a few minutes. So considering the job life is usually tens of minutes or tens of hours. So this efficiency is sufficient for practical use.
Thank you. Any other questions? Okay, so if no, so we can conclude the talk. Let's thank the speaker again.
Thanks.
We have the last presentation. The paper is wrapped. And the speaker is Zhang, who is a third-year PhD student at UC San Diego, working with Professor Yu-Fei. His research focused on high-performance system design and end-to-end optimization for deep learning, particularly for deep learning-based recommendation models and the large language models. Okay, let's start.
Thank you very much for the introduction. Today, I'll be presenting our work, which focuses on optimizing the training and the input preprocessing pipelines for recommendation models. Deep learning-based recommendation models are widely adopted across various applications, whether you are shopping online, browsing social media, or listening to music. The recommendation model will provide content tailored to your interest, which will significantly enhancing the user's experience. Basically, a recommendation model processes user request and content information as input and outputs the user's click-through rate for the given content. However, during the deployment of recommendation model, new users and contents are continuously entered the system, and the user behaviors or preference may shift over time. This will significantly affect the prediction of the click-through rate and decrease the quality of the recommendation. So To mitigate this problem, the DLMs in the industry follows an online training approach. And here's the workflow of the online training. First, the new training data are continuously generated and collected from the model survey node. And secondly, the raw data are preprocessed in the input preprocessing node and converted into tensors. Lastly, the model training node uses this tensor to train the recommended model, and then update the models in the survey node. To prevent data store in the online DLM training, the current approach allocates many dedicated computing nodes for input preprocessing, which significantly increase the power consumption. And this figure breaks down the power consumption of main components within the online training pipeline at Meta. Meta reported that the data storage and input preprocessing has already consumed more power than the GPU trainers in its data center. Therefore, optimizing the input preprocessing of DLM is crucial to enhance the training efficiency and reduce the training cost. Before we dive into the optimization strategy, let's first take a closer look at DLM. Typically, DLM consists of three main components: embedding table, bottom dense layers, and top dense layers. The bottom dense layers process dense inputs such as user's age. In contrast, the embedding table handles the sparse inputs, which are often represented as multi-hot sparse vectors. And these activated entries within these vectors are used to index and retrieve the corresponding rows from the embedding table, and converting this sparse input into dense embedding features. And lastly, the top dense layers utilize these features to perform feature interactions and generate the predicted click-through rate. During the DLM training, the dense layers, including both the bottom dense layers and top dense layers, are duplicated across GPUs and trained using data parallelism, since these layers are compute bound and small enough to fit into a single GPU. And regarding the embedding tables, they are usually be sharded and across multiple GPUs and trained with model parallelism, as the embedding table typically require hundreds of gigabytes or even terabytes of memory, which is far beyond the memory capacity of a single GPU. And with model parallelism, each GPU only holds a portion of the embedding tables, so auto communication are required for the lookup the embedding in the forward phase and for synchronizing the gradient, embedding gradients during backward phase. So this auto communication are fully exposed in the critical path of DLM training, which means the computing units of the GPU are actually idle during these communications. So the memory-intensive embedding layers and the auto communication for embedding leads to periodically fluctuating GPU utilization during DLM training. And this figure illustrates the profiling results of a GPU utilization when training a DLM on 4 A100 GPUs. It can be observed that GPU utilization stay high during the execution of the forward and backward of the dense layers. And conversely, the GPUs are underutilized during embedding computation and communication. And this fluctuating GPU utilization provides a unique opportunity to optimize the online training pipeline for DLM. So how can we leverage the remaining GPU resources from the DLM training for input preprocessing? Actually, this is not trivial to achieve due to several challenges. So firstly, GPUs are inherently less efficient when performing diverse lightweight input preprocessing operations. This figure shows an example of the input preprocessing graph, which contains several input preprocessing operations to generate an input tensor. And these operations are usually element-wise and lightweight, but GPUs are designed for large compute-intensive tasks like matrix multiplication rather than this small diverse operation. So if we sequentially launching the small input preprocessing kernels on GPUs will result in significant kernel launching overhead and waste the computing resource of GPUs. And secondly, there will be a potential for a resource contention between the DLM training and the input preprocessing. Given the fluctuating GPU utilization during training, if we simply co-running the DLM training and the input preprocessing will lead to resource contention, and which will increase the latency of each training iteration. So to efficiently leverage the remaining GPU resources, we first propose a horizontal kernel fusion technique to overcome the challenge caused by lightweight input preprocessing operations. And this figure shows the input preprocessing graphs of 3 different input features. In this graph, we can identify several opportunities for kernel fusion. For instance, we could fuse the 2 secret hash kernels and the 3 film kernels to better utilize GPU. We refer to this as horizontal kernel fusion because it is different from the traditional kernel fusions, which combines the successive kernels and aim to minimize the data round trip between the slower GPU HBM and the faster SRAM. So given the design of our horizontal kernel fusion, the next step is how to define all possible horizontal kernel fusion within the given input processing graph. This is challenging due to 2 reasons. First, the fusion is constrained by the date dependency. For example, the 2 first X operations here cannot be fused together due to their date dependency. And second, some fusion opportunities conflict with each other. For instance, if we fuse the first X operator here, then we cannot fuse the 2 secret hash operator here. So to overcome these challenges and efficiently search for all possible kernel fusion opportunities, we formulate this searching problem into a mixed integer linear programming. And the objective is to maximize the total number of kernels being fused. And we have to subject to the constraint that ensures the correctness and the data dependency and to avoid the conflicts. And by solving this MILP, we can efficiently obtain a kernel fusion plan that fuses as many kernels as possible, which will give us better performance. And next, to avoid resource contention, we propose a resource-aware mapping and co-run scheduling method. Basically, we have the input preprocessing graph of many input features, and we also have a DLM trained across multiple GPUs. So to share GPUs between the DLM training and the input processing, we need to address 2 key questions. So first, which GPU is the optimal place for executing a given input preprocessing graph? And second, when should input processing operation be executed? In other words, the input processing operations should be co-run with which DLM computation to avoid resource contention. So to answer the questions and get a co-run schedule that maximizes the training efficiency, our method first starts with mapping the input preprocessing graph to the GPU. So initially, we will assign each graph based on the data dependency. As shown in the figure, the graph marked in blue will preprocess the input for the embedded table 0, and it will be assigned to the GPU 0, which is where the table 0 is located. If the input graph is not co-located with the state consumer, just like the graph marked with red here, we need to fetch the input from GPU 0 to GPU 1, resulting in additional input communications. So next, based on we solve the MLP to obtain the horizontal kernel fusion plan on each GPU based on the mapping from step 1. And then we will schedule to co-run the DLM training and input processing in a resource-aware manner. The key objective here is to avoid resource contention. And to achieve this, we designed a cost model to evaluate the candidate co-run schedule efficiently. So it will first estimate the overlapping capacity of each DLM training operations. It is achieved by offline profiling each DLM training operations, measuring the largest kernel it can be overlapped with without increasing the latency of the training itself. The key insight here is that both the overlapping capacity and the latency of the input preprocessing kernel measures the error in utilization 10 graph. So we can use the latency of the largest kernel that it can be overlapped with to measure the overlapping capacity of a DLM training. And next, we train a latency predictor for the input preprocessing operation to efficiently predict the execution latency of a given input preprocessing kernels. And with these 2 components, our custom model can efficiently estimate the exposed input preprocessing latency for a given co-running schedule of a training operation and preprocessing operations. And then based on the exposed latency estimated from the step 3, we could remap the input preprocessing graph from the GPUs with the highest exposed latency to the GPU with the lowest latency, which will balance the workload between GPUs. And we will repeat the step 2 to 4 until no further improvement can achieve. And our method will identify the mapping and co-run schedule that minimize both the input communication and the exposed input preprocessing latency. So to evaluate the performance of RAP, we choose 2 kind of baseline. The first one is touch arrow, which is a CPU-based Python data frame library released by Meta. And besides this CPU-based baseline, we also implement two GPU-based solution utilizing two widely adopted GPU sharing technique, CUDA string and NVIDIA multi-processing services. And to comprehensively evaluate RAP with two input preprocessing plan. For plan 0 and plan 1, we follow the default plan for criteria terabyte dataset provided by touch arrow. And to test the RAP on larger datasets with more complicated input preprocessing graph, we randomly generated two larger preprocessing plan, plan 2 and plan 3. And the end-to-end performance evaluation, it can be observed that RAP consistently outperforms all baseline on all experiment settings. And RAP achieves 17.8 times speed up over the CPU-based touch arrow, which indicates that if we only use the CPU computing resource within the training node, it is insufficient for the preprocessing and will lead to data store. And the RAP also outperforms two GPU baselines, which showcase the effectiveness of our optimization. And we also conduct a speed up breakdown and the optimality analysis of RAP. Besides the full version of RAP, we create two additional settings of RAP, which remove one of our optimizations. And we then compile these settings against three baselines. The sequential, which executes the DRM training and input preprocessing sequentially on the GPU and fully exposing all input preprocessing latency. And MPS is which leverages MPS to overlap input preprocessing with DRM training. And ideal is the ideal case that all the data has been offline preprocessed, and so there will be no input processing latency and input communication latency. And the result in the figure shows that the improvement of our individual optimizations. And additionally, it can be observed that the end-to-end performance of RAP is very close to the ideal case. This implies that input processing are almost perfectly overlapped with the DRM training without compromising the training efficiency. Thank you for listening to my talk, and happy to take any questions.
So is there any question from the audience? Yeah, please come to the front.
Nice talk. I'm wondering if it's more reasonable to disaggregate the input processing and the computation to CPU and GPUs individually. Because I saw in your baseline, you compare with torch arrow, which means you run all the tasks on the CPU instance. So what if you disaggregate them on different resources?
Yeah, this is a good question. So, so basically, we first try offload all the preprocessing offload workload on GPUs, and we found that GPUs has sufficient resource and capacity to do all this preprocessing. So if we in other cases, if we have many very heavy preprocessing workload, maybe we could combine this to use both the CPU and the GPUs.
Okay, thanks.
Yeah, thank you.
Hi, Tom from Hawaii. Question about your fusion algorithm. So in you basically stated that what you want to do is minimize the number of resulting kernels at the end of the process, but not all kernels are created equal, if you pardon my phrase. In a sense, some will have different resource utilization, some will have different throughput. Have you considered using properties of the kernels in your decisions to optimize which ones get merged as a priority versus over the other ones? And if so, has that resulted in any change in performance?
So basically, we currently only consider to fuse the kernels with the same type. We don't consider a fuse the kernel with different types. Since if we consider a fuse different type kernel, we need to generate there are too many combinations, and we need to generate this CUDA code to recompile this. So we only search for the kernels with the same type to reduce the search space and reduce our searching cost.
Okay, so you kind of misunderstood my question because you had a conflict case. Remember?
Yeah.
Where you had like one kernels that you fused, then you have the other, right?
Yeah.
So whichever one you fuse, the number of kernels is going to be the same, but each of the kernels may be different in their properties. So that's what I meant.
Oh, yeah. Okay. Sorry. Actually, we have the weight for each kernel. So as you mentioned, a few different kernels bring different benefits. So we have a way to indicate this in the cost model.
Okay, thanks.
No other questions? I think this concludes this session, and let's thank all the speakers again. So we are perfectly on time. Yeah, thank you.